Just before Eric starts, Eric has contributed materials to Symbiote, and he and his wife co-authored one involving chemical engineer, and she posted it in Spanish as well as in English. We have, maybe a dozen versions of Spanish modeling scenarios, some of which are due to my colleague Norma Miller, who's talking later from Panama. But that was a very nice one. And his wife is working in industry. And well, you're working in industry, but it's just a different kind of industry, right?
Different kind of industry, yeah.
So let's get started. As Eric Stachura, and he is at Kennesaw State University, and you're on.
All right, thanks, Brian. Yeah, so I was thinking hard about what to talk about today, and it's going to be a very unique talk. I'm glad to have the opportunity to not give the standard kind of technical seminar talk. I'll talk about some technical details, but I'll also be fairly informal and leave some time for conversation and hopefully get some ideas from other people and just be less strict and less technical. So Kennesaw State, we're in Kennesaw, Georgia. One of the things that the city of Kennesaw has is what they call the big chicken. It's literally a big chicken. It's a KFC on the street. They have a chicken that's probably 30 feet tall. Its beak moves, its eyes rotate. It's quite a phenomenon to see. So that's the first thing that they told me about when I heard about Kennesaw and moved down here, is the big chicken in Kennesaw. I think it has its own Wikipedia page too. So okay, so what I'll talk about today, I'll talk about an undergraduate differential equations project. And then I essentially want to stop with that and talk about a bigger notion of success versus failure. So this is an interesting thing I've been thinking about lately, and how does one actually define success? So that's kind of how I'm gonna go today, and hopefully it won't be too technical, but we'll start with the technical stuff first. So, and then I'll wake you up after that boring technical stuff, and we can have a more informal conversation. All right, so we were interested in this, essentially looking in 2 dimensions at Maxwell equations, and this thing looks kind of scary. You have a vector field, you have the curl appearing twice. In vector calculus, you may have seen curl of a vector field, but taking curl twice is kind of a weird thing, but curl is a vector, so I guess you can take the curl of it. And so we were interested in looking at this in 2 dimensions in a polygonal plane. So we're essentially motivated by understanding how electromagnetic waves scatter off of corners. So we tried to simplify this down. Our first simplification was to get rid of most of Maxwell equations, because that's a hard system to deal with. So we'll try and reduce it to 1 equation. But it turns out this is still pretty hard. So we try and reduce it even further and get us to a system of ODEs, which is still pretty hard, but we're able to actually say something there. So eventually we'll get to the ODEs, but we start off with this scary looking vector calculus problem, but we'll eventually get it to a nice system of differential equations. So it turns out by using some vector calculus identities and a clever use of polar coordinates, we can also similarly study just essentially Poisson equation in 2 dimensions. So we reduce somehow the complexity of this bicurl operator into the classical Laplace operator in 2D. So what's causing the issues if the differential equation itself is in some sense nice? Well, what's the issue which we were interested in is the corner itself. How is that affecting the problem? So make the differential equation nice, just focus on the difficult geometry that's hard enough. So we were looking for a vector field U, and we work everything in polar coordinates. And so we're actually able to reduce our problem to a system of PDEs, which seems more difficult, but it's actually simpler. But still, systems of PDEs are still pretty hard to solve. But it turns out that just like you make and I just taught this the other day in differential equations, if you make an appropriate substitution, then you can actually simplify your life if you make the right substitution. So if you make the right substitution, we can actually reduce this to a nice system of ordinary differential equations. So we can get rid of all our partial derivatives and reduce it to a system of ordinary derivatives. So still a system, so perhaps still a little difficult, but we're able to reduce the complexity step by step. And so what is it that we're guessing? And I'll kind of motivate this in a second. So we kind of guess a product. This is kind of like separation of variables. I also just taught this in my PDE course. In polar coordinates, you guess one function of r times one function of theta. You make this classical guess, a product of one function of each variable. Then you plug it back into the differential equation and you see what you get. So essentially, this is kind of what we're doing, except we're going to have infinitely many terms. And we choose to have trig functions. We have sine and cosine of the angle with some coefficients in there. And I'll talk briefly about what these coefficients might be related to in a second, but there's some numbers, and we're going to get a system of differential equations for the radial coefficients. So after making a whole bunch of simplifications, making all these nice guesses, we are finally able to reduce to a system of ordinary differential equations, which I give you here. And you'll see it's still pretty involved. So we still would like to say something, simplify a little further to get any kind of explicit solution that we can. And it turns out you can. If you make another transformation, you can turn this into something that's pretty simple. It can be done by hand. It's quite lengthy, but we use Mathematica a lot to help us simplify our calculations. So starting from this complicated, well, first starting from the full Maxwell equations, we're able to eventually reduce it down to a system of two ordinary differential equations, which under a nice transformation can actually be solved explicitly. So anything explicit when I'm working with undergraduates is very nice. They don't like the abstract. There exists the solution. It's nice to get our hands on an actual concrete solution. So this is one way we can do that. So what was the goal here? Why are we trying to do all of this? So we wanted to capture the singular nature of the solution. So this is actually a classical topic. So let me just give you some insights about this. Suppose you have a differential equation in 2D. 2D is hard enough. So given just a differential equation in 2 dimensions, suppose that your geometry is just an angle, a wedge, say a pizza slice. That's what my student used to call it, a pizza slice. And so we're interested in the behavior of the solution as you get close to the corner. So you suppose you have some angle, we'll call it omega. Then it's classical stuff that you can split the solution of your differential equation into a nice part, where nice is, okay, you can get technical. This is nice in the sense of Sobolev regularity, but this is essentially as nice as you want, plus a singular part. So you get a sum of two parts, a nice and a singular part. We were interested in studying the singular part. So at least for nice differential equations in the sense of like a Laplace equation or elliptic equations, in polar coordinates, this typically looks like the following, the singular part. Looks like a power law, looks like r to some power times some trigonometric function of the angle theta. And what is this coefficient now here? Here's the coefficient that is related to the geometry, which is interesting. Here's how the geometry comes in. So the coefficient goes like pi over omega, where omega is the angle. So essentially, it turns out what matters is if this coefficient is bigger or smaller than 1, which means, is your angle bigger or smaller than pi? So this is classically, this is well-known stuff. We were trying to get some kind of similar result for something that's a less classical differential equation. What's interesting is this omega equals pi case, there's kind of no singularity, because if you take an angle equal pi, you really just have an upper half plane kind of thing. So there's actually no singularity. You have a flat geometry. And I just wanted to give you one quick example. So the size of the angle, like I said, plays quite a role in how the solution behaves. So in the simplest possible case, you just have the classical Laplace equation, let's say with nice enough boundary data. Then it turns out that you only have a contribution to the singular part. Otherwise, you have just a nice classical solution with no singular nature. The only contribution comes from those angles that are larger than pi. So these are non-convex angles. So for example, I chose the angle 3 pi over 2, for example. You go 3 pi over 2. And your singular part looks like the radius r to the power 2/3 times sine of 2 over 3 times theta. So this is all kind of classical stuff. And this is kind of what we were hoping to get. Try and see what is the power that we get and what is the coefficient of our trig functions, if we could do such a thing. So that was our goal. But all of this at least for classical differential equations, is pretty well known. There's this nice book by Grisvard, published by Siam in 2011, which I refer you So lots and lots of interesting, quite technical things in that book, but this is fairly apparently well-known stuff. All right, so now here's where the twist comes. What happened? The answer is I don't know, because we didn't get much further than this. So this was at, in some sense, the height of the pandemic, whatever that may mean. This was in 2020. But I just wanted to point out what were some of the things that the student was looking at in order to get up to this formal setting and the understanding things in a nice sense of Sobolev regularity. Well, we were looking at definitions of the geometries and giving some explicit examples. Looking at some operators that you may have only glanced at in your calculus class, like gradient and divergence, and there's this nice identity with curl and how it relates to vector Laplacian. But also she was able to increase the sophistication by looking at things like weak derivatives and looking at bilinear forms and how you solve the Laplace equation using the Lax-Milgram theorem. So this was a slower going process because Lax-Milgram theorem just tells you that there exists a solution, whereas my students typically like to have something concrete. Okay, that's great. What is the solution? There existed. What is it? What can I plug it into the computer? But we still got there. We still talked about how we proved things, what you need to prove in order to use Lax-Milgram theorem. So we were able to go still a good deal along the way and talk about LaTeX as well and in there. So this was an interesting project for me in the sense that it kind of fizzled out. But then I went on, eventually I heard the student went on to study somewhere else with a different professor, studying something wildly different, gerrymandering. So this was actually quite an interesting time to do this. So again, we're in Georgia. So if you've heard in the news, perhaps in the past few years, we have been up there in the news for various political things. So gerrymandering was a hot issue just a few years ago. So the student went on to study some gerrymandering problems at KSU. And this is actually this really nice program that we have at Georgia called Posters at the Georgia State Capitol. This is an event at Atlanta. So Kennesaw is not that far from Atlanta, 25-minute drive, not so bad. So it's an annual event downtown in which the undergraduate researchers from schools in Georgia, they can come and present their research as posters and meet various state legislators and staffers there. So this is a really cool event. And unfortunately, I mean, she didn't go and present our interesting differential equations work, but she was able to still talk about her interesting gerrymandering work with a different professor. So instead, she got kind of two different experiences with two wildly different topics. And although she didn't continue with differential equations, hence the title Passing By, we just moved on by differential equations and went on to the perhaps more attractive gerrymandering notion at the time. She did get nice experience with two different research fields. And I think this is a really great program that we had. I wasn't aware of it at the time, but this posters at the Georgia State Capitol where students could actually go to the state capitol in downtown Atlanta and talk to legislators about their mathematical research. So this was an interesting trajectory the student had. So I just kind of outlined this idea. So she started as a business major and took Calc 1 with me in my first year. So she started when I started. And somehow ended up taking some calculus of variations course with me. Then she became the president of the KSU chapter of the Mathematical Association of America. That was before she was even a math major. And then at some point she decided math is for her. Maybe not differential equations math, but that's okay. And she went on to apply to graduate school to pursue her degree in math. She got accepted, and now she is pursuing her PhD in math in graduate school. So she'll be finishing her first year this spring. So an interesting trajectory, starting as a business major, going through calculus of variations, where there's a lot of differential equations, going towards gerrymandering, but nonetheless aiming her towards a graduate degree in math. So an interesting trajectory. So I recently talked about some of this stuff at the joint math meetings in Boston and had some interesting conversations about the notion of success. Because what do we think about success? Maybe success is classically, at least in some sense, maybe a peer-reviewed publication after you put in a bunch of work, you write a paper, you get a peer review to get accepted, and you get some nice result. So this didn't happen in this case. This kind of fizzled out, and I still don't really know the answer to the problem. but perhaps this is okay for the moment. And I would argue that this experience was still a success for the student. Even though she didn't go on to pursue written differential equations even further, she didn't write a paper that ended up in the annals. She still continued math in some sense, got some great exposure at this posters at the Capitol program, and eventually decided to go for her PhD in math. So now the technical and the formal part is over. And now my question, both to students and faculty, and I genuinely have questions. I don't have the answer here, but perhaps we can have some kind of at least informal conversation, or you could write it in the chat. So here's one question. Suppose you spend as a faculty member, suppose you spend all this time working with a student, you invest your time and go through all of this work, but it doesn't necessarily end up with some nice, clean deliverable that you can point to. So the first question I have is, how might one justify this experience in some sense that doesn't necessarily result in a very nice concrete deliverable to maybe your boss or your boss's boss, to the administration, but this was still a successful event and worthwhile endeavor of your time? So this is one question for faculty members, but also to students. I'm curious about if there's, I don't know if there's any students here. I had the question just in case. So students, I wonder if you don't end up with some nice clean result, what are your thoughts? Are you necessarily disappointed? Are you happy with the experience nonetheless? Would you have preferred things go differently? So these are two questions that I'm curious about. And maybe I'll just open the floor or open the chat to people and have some brief discussion about what you think might happen, or how we might still be able to prove this is a successful endeavor, even if it doesn't result in anything concrete necessarily.
Yeah, so let's wait for some uncomfortable silence here.
Sure, I can wait at the board and like in class and try and wait and then try and give some answers and try and figure it out. The problem is
any of our colleagues want to address that? It would be good if someone else would speak up, please.
Yeah, exactly. So I don't know either. Perhaps people don't know, but so I think the point I wanted to kind of make is that I think this is still a successful endeavor, even if all of the time spent didn't necessarily result in anything concrete, in a nice paper that I can show. Here we wrote this paper. This still ended up in a worthwhile endeavor for the student, and it was worth the time investment. Now, as a student, I'm trying to think back to when I was a student. What happens if I worked on a project, perhaps with the professor, and it didn't necessarily end up with something fantastic? But this is a highly personal question, I think. So for me, I was happy during my undergraduate time to just get experience, and that kind of pointed me to what I was interested in and what I was not interested in. So even if it doesn't necessarily work up in something nice and clean, you get the experience, and the experience, I think, is still an important thing for students to take away, regardless of if they go on and continue with differential equations and analysis, or they go on to more discrete math, or something in between. I think even if there's not anything concrete that arises, the experience is quite impressionable to the student. At least for me, it was when I was an undergraduate, and I have a feeling for many other students it will be worth the endeavor as well.
Well, she increased her mathematical vocabulary immensely.
Exactly.
And she learned how to talk mathematics. I mean, and thoughtfully, and the difference between an existence theorem and an algorithm to produce. When students confront that, sometimes they go, well, what good is an existence theorem if you don't have the thing, And
Exactly.
I always point out, it's like an insurance policy saying it's out there, you just got to find it.
Yeah. So this actually got me thinking with talking with our MAA students as well, and how they perceive faculty, and this is kind of related. And I was kind of surprised in some of the conversations that I had with some of our students. Some of them actually, this is kind of a dramatic statement, but in some sense, they don't understand we're humans. So they think we're machines with all the answers. And I was very surprised. I was saying, couldn't be further from the truth. I'm confused all the time. I mean, But this is somehow the impression that many of the students have. So actually, this led me to realign one of the seminars that I run to include more broader talks rather than, okay, here's some kind of differential equations you can do. Here's how you can apply this method from your class to do this type of differential equation. But we want to include talks, and we're doing this semester, about how to do math. Maybe like, oh, let's think about what happens if you get confused for a substantial amount of time. Should you just get stuck and give up? And just kind of the thought process of various faculty members is how they get stuck. But somehow the students have the impression that this doesn't happen, that the faculty don't get stuck. And I was kind of shocked by this. And so I was hoping to get more seminar talks, and we're doing this, like I said, this semester, to kind of illustrate to students that we're not machines, we are humans. We don't know everything. We're trying to learn and figure out the best way forward. And so I tell them that being confused is okay. I spend most of my life confused and not understanding how to proceed with various things. And then connecting this back to the notion of success versus failure. So what does exactly failure even mean exactly? So having students realize that even for us, it's difficult to come to terms with failure. What does it mean? I try and tell them I fail all the time, every day, whether it be failed grant proposals, rejected papers, or messing up calculations at the board in class because I forgot a minus sign, or I missed a 2 or something like this. So, but somehow they had the impression that we don't fail, or we know everything. And so that made me kind of want to redesign the seminar to helpfully illustrate to students that we are not perfect. We get confused, we still try and learn, and we got to talk to each other. And so the last question that may or may not be answered, I just wanted to throw it out there. If you guys have any thoughts about what is failure, or how can we talk about confusion and failure to students to kind of illustrate that we don't have all the answers, or maybe you guys do have all the answers and I need to learn from you. Maybe that's the way.
So what did George Polya say? Problem solving is knowing what to do when you don't know what to do. And many of us are in the you don't know what to do. Any other thoughts about? I think if you do active learning and they see you engaging and thinking on your feet, especially when a student asks, what about doing this? And you don't even know about it. You're demonstrating live that you don't know the answers. Now, I've had students accuse me of, well, you're pretending. and after they know me for a while, they realize he's not that smart and he's not pretending. He really has no clue. But the fact that they really think you're pretending is saying they buy into the paradigm that faculty know it all. And a paper or a textbook shows they know it all because they've spent all this time crafting it and organizing it. What you didn't see is, I'm told that Leonard Euler was able to get papers published in which he described failures. And only Euler could do that. I mean, he was the top of the crop there. And so I think if students see us struggling, they'll understand that it's okay. Any other experiences with struggling and students seeing us confused?
So let me add two comments, just maybe to finish up. So I actually tell other faculty and students that I really like when I mess up. I think it's a good experience when I mess up a calculation at the board in class, because I will genuinely sit there and not understand what's happening. Not only there's pressure from the students, but at the time I just, for whatever reason, can't for the life of me figure it out. And most of the time, the students are like, they wake up, figure out what's happening. I gotta pay attention now. And most of the time they help me figure it out. It's really a remarkable experience. So I really do enjoy legitimately these times when I don't do it on purpose, but of course it happens. I mess things up at the board, but they always turn out to be really great learning experiences. And not only does it illustrate to the student that I'm not perfect, it has a nice benefit. It wakes students up for some reason. I'm not entirely sure why that kind of gets them going. But they really do come together and help me figure out the problem at the board. And the last thing I always try and tell students is that you see the nice clean result that I show you. You don't see the piles and piles and piles of paper which with nonsense calculations were wrong. You get this nice clean result that I have here. You don't see all these. I can't publish a book on all of the things that I've done wrong or all the nonsense calculations that I have. But you kind of only see the nice result rather than all of the paper and all the trees that I end up killing because of all the nonsense that I write down.
So Abdi, you have a comment?
Yeah, hi. I tried to be quick. I know we're running out of time, but just a couple of comments. One is this semester I have a student who sits very close in front of the class, close to me, and he's constantly fact checking my statement on his computer. And so the other day I said there is no simple formula for the circumference or perimeter of the ellipse that we can get like the circle. And suddenly he put his hands up and says, no, ChatGPT, here is the formula. And I looked at his screen. Sure enough, ChatGPT gave him a formula close to 2 pi r, on the other side, on the ellipse side. And I said, well, that's rubbish. And we got into an argument on that. So later on, about a day later, I checked again with ChatGPT, and they've changed their tone now. Now they say, yeah, it is actually not possible. It's a numerical. Best thing is a numerical solution, etc. So I'm waiting to see him again to tell him that don't trust ChatGPT, number one.
Interesting.
The other point I was going to make real quick is that I think it's success, definitely. I reflect back to my own days as a graduate student working with my advisor on a problem that kind of similar to what you were saying. He had asked me to investigate the stress-strain relationships on an elastic material, which is pressed by a wedge-shaped punch. And this led into very complicated multi-parameter eigenvalue problems, etc., which was part of my research. And I hit a brick wall. I just couldn't get this. I tried for months. And finally he said, well, give it up because I can't do it either. And even though that was the end of that, and I still look for, leads on that whenever I can, the singularities there are just formidable. It's just, you can't bring them down. Yeah. But I learned a lot. I learned a tremendous amount. It actually led to the completion of my thesis.
Well, thank you for sharing. So we don't need to go on to true confessions, right? But I think there's a lot to be learned by making mistakes, assuming they're not catastrophic, and that you can remember those. And I thank you for bringing that to our attention.